Byron back with us. He just graduated from the machine learning department this this year. Yeah.
About a year ago.
About a year ago. He worked with Jeff Gordon over here and did some of the pioneering work on spectral methods. And now he's working with Dieter Fox at UWash, and he's going to tell us about spectral robotics.
All right, so yeah, the talk is titled Spectral Robotics. It's a little bit cryptic maybe, but hopefully by the end of the talk, you'll know what it's about. So before going much further, I just want to thank a couple of my collaborators. So many of the ideas, algorithms, and examples in this talk were developed jointly with several of my advisors and colleagues. So Jeff Gordon, my PhD advisor here at CMU, Arthur Gretton, who is at the Gatsby unit at University College London, and Dieter Fox, who's my postdoc advisor, and he's a roboticist at University of Washington. Okay, so this talk is going to be about combining machine learning and robotics. And of course, many people use machine learning in robotics. People use it all the time. But usually this takes the form of some off-the-shelf black box method, like support vector machines or something like that, to solve some small subpart of a much larger and more complicated problem. And in this talk, I'm going to talk about, sort of take a different perspective on this. I want to talk about approaching certain types of robotics problems from a purely machine learning perspective. And I want to get started by telling you about this old problem in AI. So old being 1984, but this is a problem which was proposed by Ron Rivest at MIT. And the idea is this. So imagine you have some robot, or as he called it, a critter, and you put this critter into some unknown environment. And the robot can take actions, and the actions induce unknown dynamics in the environment, and the robot has no interpretation for the actions. So it really has no idea kind of what it's doing. It can just take some actions, and that changes things. The robot also has sensors, but no interpretation for what the sensors mean or how the sensors relate to the environment. And the problem is then, how do I program a robot like this to learn some predictive model from experience? So what I mean by this is, if the robot takes an action or takes some sequence of actions, the robot needs to be able to predict what it will see in response to these actions. And this is without regard to the type of sensor that the robot has, the type of actuators the robot has, or the environment, right? So the robot has no knowledge of any of this. Can you just learn a very sort of general generative model in this situation? So the goal is to learn a predictive model of the system. And as you can imagine, this is a very difficult problem, and I'm not sure anyone has come close to really solving it. But it is, I think, a good motivating problem for machine learning researchers and roboticists. So this is one of the problems which motivates me in my work. I must say, though, that today this problem is actually much harder than it seemed to be even in 1984. And what I mean by this is that in the original problem, it was assumed that the robot could only execute a small number of discrete actions or receive a small number of discrete observations. And it was also assumed that there was no noise in the actions or observations. And these are completely unrealistic assumptions for today's robots. So today, robots are complicated by this sort of wide variety of sensors and actuators that they use. And I'm showing you some of them here. These are just sensors that I've been using in my own work. And there's a wide variety of them. So for example, there's a laser rangefinder up in the upper corner. There's a radio beacon here, which can give you range from time of flight radio information. Of course, there's the Microsoft Kinect, which is used on all sorts of robots now. So this gives you depth information at 30 frames a second. Stereo cameras. Grippers now have higher resolution touch sensors, which give you high resolution idea of the pressure when it's gripping an object. There's also motor encoders and joint encoders, which tell you about the configuration of manipulators and hands and things like that. And finally, the blue box over here is an accelerometer, which or it's an inertial measurement unit, which has an accelerometer in it and a gyroscope in it. So you can imagine these are all really, really different types of sensors. And so what do you do? Like, what do you do if you want to learn a predictive model? and you have all these different sensors. Well, what people do is they've basically designed many special purpose tools to solve various predictive modeling problems. So for example, there's structure for motion and vision, simultaneous localization and mapping, which is applied to many robotics problems. And there's also things like system identification to learn models of stochastic processes or dynamic systems. And I guess, like, I look at this list, and all of these things are very cool on their own, but I'm a little bit disappointed because they're really solving just very special cases of this more general learning problem, this kind of dream that people had 30 years ago. And so I guess what I want to know is, can we actually come up with a framework for solving the critter problem? And if we come up with a good framework for this, some good machine learning algorithms, can we then solve all of these other things as just special cases of a much more general problem? So that's the idea. Here I'm showing you a whole bunch of different types of data sets that I've been working with. And these are the types of data that I'm trying to apply my machine learning algorithms to. You can see that many of them are really high-dimensional data sets. They have high-dimensional observations. Some have control inputs, like the robot arm or the robot camera. Others do not, like the smoke and fire. Some have very short training data sequences, and some have very long ones. And some can be modeled fairly well given known physics, like the pendulum or the robot arm, and others cannot. So the smoke and, for example, flight trajectories for this moth are actually better modeled as stochastic processes. So there's this really wide range of problems and wide range of data that we're trying to consider. Now, I'm not going to talk about all of these examples in detail today, but I do want to focus on some subset of them. So I've basically selected 3 problems here, and I've selected these problems because they are very, very different types of predictive modeling problems. They have very different types of sensors and very different types of robots. So first we have range-only simultaneous localization and mapping, which is using range from radio information. Video textures, which is just a camera looking at smoke rising from a grate or other sorts of kind of stochastic natural phenomena. And finally, depth camera and manipulator, which is a Kinect depth camera looking at the manipulation space of a Barrett WAM arm. So I'm going to look at these 3 examples over the course of this talk. Okay, so I'm going to start out, though, by talking a little bit about spectral learning, what spectral learning is, and then we're going to see how we can use spectral learning as a framework for solving these seemingly very disparate problems. So again, the idea is that rather on relying on sort of expert knowledge of a system or the physics behind a system, we're going to take a very different approach. Okay? So we're going to think of our model as a predictive model of the system. So this is going to be more of a statistical approach to modeling these different types of data. And I guess this is what I mean by a machine learning perspective on robotics and robotics problems. So instead of trying to model the physics which underlie things, we're going to think about all of these different types of data as maybe samples from some stochastic process, and we're going to try to learn some model in that way. And connecting back to kind of Revest's critter problem, this idea of a predictive model is, I think, very natural. We want to say, like, given that I execute some actions, I want to be able to predict what my sensor will return in the future. So in particular, I'm going to define the state of a model as the expectations of features of future observations given history. And that's going to be our sort of general idea of what the state of any of our models of these systems will look like. Now, this notion of state is actually very, very general. It includes controlled stochastic processes like Kalman filters. So you can show that Kalman filter models, which basically represent state as a Gaussian distribution over some latent state, are equivalent to modeling a stochastic process with a Gaussian distribution over future observations. This is also true with input-output hidden Markov models, except it's a multinomial distribution. So many stochastic processes model state exactly in this way. This idea that state is, again, expectation of future observations can also be interpreted geometrically, and it's possible to show that structure for motion and simultaneous localization and mapping, at least for specific problems, have state which also can take this form. So that's kind of the idea. The state of any of the systems that we're going to try to model is going to be basically a prediction of future observations given a history. So the second thing we need is, in addition to state, we need some way of updating the state. So if we have some state at time t, and we see a new observation or take a new action, we need some way to update the state to time t plus 1. And what this means is we basically need a dynamical system model. We need some model of dynamics which allows us to update state given new actions and observations. So a dynamical system uses generally a recursive rule to update state like this. And so, for example, if the state is a probability distribution on future sequences of observations, the recursive rule will generally be Bayes' rule. And so this gives us a Bayes filter, which is a pretty common way of modeling stochastic processes or modeling your distribution over state in robotics. All right, so that's the basic setup. We're going to think about state as a prediction of the future, and we're going to need some dynamics which allow us to update this prediction of the future given new observations and new actions. And together, these two things will allow us to make predictions about what we're going to see in the future. So the next question is, how do we actually learn a predictive model from data? So there are many ways of learning dynamical system models. For example, maximum likelihood or gradient descent. But I'm going to suggest something a little bit different today. I want to talk about spectral learning. So what is spectral learning? I know a few of you work in spectral learning, so you guys know. But for those of you who don't, spectral learning has nothing to do with ghosts. The key idea is that for many types of systems, the eigenspectrum of predictive moments can be related to the inherent structure of the process which generated the data. And we can use this relationship then to learn a good predictive model of the process. So that's the basic idea, and over the next several slides, I'm going to talk about this in a little bit more detail, and you can see exactly what I mean. Okay. Before I go into the details of spectral learning, though, I just want to say a few things about why spectral learning algorithms are nice, and they have very good theoretical properties. So in contrast to methods like maximum likelihood, spectral learning algorithms have a huge advantage, which is they have no local optima. And this results in a huge gain in computational efficiency because we don't have to search the space of potential solutions as exhaustively. We do have to trade this off, though, against a slight loss in statistical efficiency. And this is basically due to the fact that spectral methods are sort of a method of moments-based approach, which is generally less statistically efficient than maximum likelihood methods. However, that is a trade which we almost always want to make. And in practice, it's often very, very difficult to learn maximum likelihood models, especially for dynamical systems, which converge to an actually good model which works well. So even though we have this slight loss in statistical efficiency, the spectral method produces models which seem to work much better in practice. Okay, so let me talk a little bit more about spectral learning in detail. The basic insight, really, for any dynamical system modeling problem is that you can think of state of a dynamical system as basically a predictive compression of the past. Or maybe a little bit more formally, state is generally a statistic of the past which is sufficient to predict the future. It's basically just what state is. So I think this accords well with our notion of state, which was inspired by the critter problem, right? It's, we want to have some prediction about what's going to happen based on what we've seen so far. So to be a little bit more specific, we're going to assume that predictions of the future from the past actually factor according to some basis, which I'm going to call gamma here, and a lower dimensional state. So essentially what I've written down here is we have the expectation of some sequence of future observations given a history. So that's the first part of the term. And we're going to assume that there is an underlying model where this factors. And we can then write the model down like this, where we have some basis gamma and a lower dimensional state, which will just be an expectation of this lower dimensional state given a history. And the property that predictions of future observations factor like this is actually a very common one. So this is not a strong assumption. So for example, in Kalman filters, hidden Markov models, and many other types of dynamical system models with latent state, you can show that the predictions factor in exactly this way. Finally, just to kind of drive the point home, empirically, if we have a whole bunch of predictions of the future, I'm calling these y hats. So you can think of this as we have this matrix of predictions of the future. The features, so each row corresponds to a feature of the future, and each column corresponds to a data point. So each column here is in y hat is a prediction of the future. And you can show that this matrix basically factors according to gamma and to this low dimensional state. Unfortunately, there may also be some noise in our predictions, so the factorization might be a little bit more difficult than it seems at first. But the predictions have this basic structure, right? We're going to try to predict the future, and then we're going to look at eigenspectrums of moments of the prediction in order to recover a state.
The long dimension there is successive states.
Oh, sorry. So the long dimension is, these are data points. They're not necessarily successive. So we're just saying if we have a whole bunch of predictions of the future, we expect those predictions to factor according to a basis and an actual lower dimensional state.
I'm asking a very simple question about the yellow box on the right.
Yep.
So
each column of the yellow box on the right is a particular, is a state
okay, that's right.
at some time point, but like columns which are right next to each other are not necessarily related. Not necessarily. In practice, often they are, but you know, okay. All right, so you know, if the model actually factors right like this, in practice we can just try to, you know, we make some predictions and we can try to factor the predictions using a method like a thin singular value decomposition or something like that. However, before we just, you know, sort of run away and do that, I want to note that this factorization is actually only defined up to some similarity transform for some invertible matrix S, right? So if we have some invertible matrix S, we could put, you know, S inverse times S in between these things, and there's potentially an infinite number of different ways that this matrix could be factored. So if we want to find a very specific state representation, so let's say that the state corresponds to, you know, some physical quantity, then we have to do a little bit more work than simple factorization. Often this is actually doable for many problems. For now, I'm going to kind of ignore this fact. And the reason I can do that is because we're going to think of S times X hat as, no matter what S is, as basically a viable state. And the reason for this is because S times X hat is what we're going to call a predictive state. It means that if we have S times X hat and we also have gamma times S inverse, we can just apply gamma times S inverse to that state and still get back a prediction of future observations. So if we care about making predictions, and that's our primary concern, then that's fine. If we care about interpreting the state in a very specific way, then we often have to do a little bit more work to learn what the similarity transform is. Okay, so the key to revealing the state is now just going to be an eigendecomposition of the covariance of predictions. So if we let sigma yy be the covariance of predictions, then it's not difficult to show that it factors according to the covariance of state in our basis gamma. And if we compute the eigendecomposition of sigma yy, we can use u, the eigenvectors, to recover a linear transform of the state estimates. So basically all we have to do is we take our predictions, our y hats, we apply u transpose to that, and you can show that this gives us some linear transform of our low dimensional state back. And this linear transform is actually invertible. You can show this because u transpose times so you can show that u transpose times gamma is invertible because we found u by this eigendecomposition, and so u is sort of necessarily the range of gamma. The second thing is that u, the eigenvectors, actually are the linear transform of the state estimates. Okay, and this is almost by definition after this first line, right? So just by doing an eigendecomposition of the covariance of predictions of future observations, we can recover a transform of the low dimensional state and a transform of the basis. And this yields a very simple learning algorithm. So basically what we're going to do is we're just going to predict future sequences of observations or features. We're going to build an empirical covariance of the predictions. We're going to factor the covariance via an eigen decomposition, and we're going to then use the eigenvectors to recover a state space. And finally, it's possible to show that this algorithm is statistically consistent. So sigma yy converges via the law of large numbers. This means that the eigenspectrum converges, and for many problems, only the top eigenvalues are non-zero because we've made some assumption about the underlying model which generated the data as being low rank. And finally, yeah, so that's basically it. So you can show that this is a statistically consistent learning algorithm for many types of problems. Okay, so that's the general idea. It's actually fairly straightforward. What I want to show you for basically the rest of the talk is how we can apply this idea to several specific problems and show that we can learn good models of these various types of problems, again, just using this fairly simple approach. Okay. So the first problem that I want to look at is range-only SLAM. Okay. So let me just begin by giving an overview of what range-only SLAM is. So SLAM stands for simultaneous localization and mapping. And the idea is we have some robot which is moving around some environment, and the robot measures distances from its current position to landmarks in the environment. So these landmarks are just going to be fixed beacons. And we assume known correspondences, which means that we assume that we know which range corresponds to which landmark. What we don't know is where the landmark locations are or where the robot is in the environment. So we want to try to recover these two things. So here is the setup. This is the data that we're using. We have a whole bunch of range information which is captured from a lawn mowing robot from CMU's Field Robotics Center. You can see the robot in the three pictures up here in the upper part of the screen. It's just the kind of giant autonomous lawnmower. And down in the lower part of the screen, you see there's these like four little squares. Those are the landmarks in the environment. The light blue path is the path that the true path that the robot is taking through the environment. And every time you see a little red beam, the robot has received range information from one of the sensors. From one of the landmarks. And you'll notice that the range data from the landmarks is actually quite sparse. It's not receiving range information at each time step. And actually, these ranges are often a bit noisy. All right, so why is SLAM an important problem? So for those of you who are not roboticists, you may not know this, but if a robot is moving around in an environment, usually it could try to track its position using odometry data, but this odometry data sort of has this compounding error effect, right? As it moves, it's measuring how far it's moved, but at each time step it has a little bit more error, and over time its expectation of its position is way, way off what its true position is. And you can see this starting to happen in the environment. So the light blue path is again the true position of the robot, and the pinkish purplish path is the position as estimated by the robot's odometry. And if you let this run for a while, you can see that the robot's estimate of its path ends up being way, way off. Okay, so what you need to do is to correct this problem is you need to reference something external to the robot. And this is where looking at landmarks or looking at the environment comes in the SLAM problem. So in this case, we're going to be looking at range from radio. And the thing is, the thing about range-only SLAM is basically if we can estimate ranges to landmark locations via, let's say, a radio beacon, and the landmark locations are known, then it allows us to really easily triangulate the robot's position, right? So we just have ranges to these four landmarks. We can easily find out exactly where the robot is. However, we may not know the actual locations of the landmarks. But conversely, if we know successive positions of the robot, we can similarly triangulate positions of a landmark. So if these three circles here are successive positions of the robot, and we know where those are, we could easily triangulate the location of one of our landmarks. The problem is, in range-only SLAM, we don't know either, right? We only have this range information. We don't know the positions of the landmarks or the robot locations. So how do you find this? Well, it turns out that you can actually get at this information by factoring a matrix of squared distances. So here, if we build up a matrix of squared distances where each row here corresponds to a landmark, and each column corresponds to a robot position at a particular time step. And we fill in all these squared distances. So here, okay, so for example here, this is the squared distance from the robot at time step 2 to landmark 1, right? And if you look at this squared distance, and you just write down the distance like this, you square the two terms, you rearrange a little bit, you can show that the squared distance actually factors into a multiplication of features of landmark positions and robot positions. And what this means is that our large matrix of squared distances actually factors into two smaller matrices, where the left factor contains landmark positions, or the map, right? And the right factor contains robot locations. So if we could just apply a singular value decomposition to this matrix of squared distances, we'd be close to solving our problem. The problem, though, is that we can't actually do this because we don't even have this matrix of squared distances, because remember, at each time step, we're only getting readings to maybe one of the landmarks, and often we get readings to nothing. So we don't have this matrix. So what do we do? Well, we're going to kind of recall our definition of state from earlier. So all we really need for spectral learning algorithms, we need this kind of expectation of features of future observations given a history. And in this problem, we're going to think about the range-only SLAM problem in this way. So given sparse training examples, which are actual range readings, we're going to use locally weighted regression to learn an expectation of the squared distances given our inaccurate odometry. So essentially what we're doing is we're sort of interpolating the missing squared distances from our local odometry information. And thinking about this from the spectral learning standpoint, now we have all of these expected squared distances, and we're going to think about these as our predictions, right? So we used locally weighted regression to make a whole bunch of predictions, and we know that these squared distances actually factor in this kind of nice way according to a map and robot locations. And so if you think of the map or this left factor as the gamma from before, and the right factor, the state as the robot locations, you essentially have exactly the same problem that I talked about originally. And again, this factorization is only determined up to a similarity transform, right? So in practice, we can try to estimate S and S inverse, and therefore recover our map and robot localization. And we can definitely do this. It's somewhat involved. I'm not going to talk about it in this talk, but you can see our paper on range-only SLAM to see precisely how to do that. Okay. So finally, what this means is we can essentially use exactly the same spectral learning algorithm that I talked about in the introduction to the talk to solve this problem. Predict a future sequences of observations. In this case, they're just squared distances. Build an empirical covariance matrix of the predictions, factor the covariance via an eigendecomposition, and recover the state space. So before I leave this topic, I just want to show you an example of this in action. So here is the actual path that the robot took through an environment. And here is the dead reckoning path, as we saw before. We can make our prediction based on our locally weighted regression. And then we just factor this using our learning algorithm. You can maybe see the little red X's, which show you how accurate the prediction is from our map factor. And now the blue path shows you the localization. So it shows you where the robot locations are in the graph, and you can see that it matches very, very well the underlying geometry of this particular problem. Finally, I want to note that this approach to range-only SLAM is as accurate and often much, much faster than other state-of-the-art alternatives, including methods like EKF-based approaches, which are specifically designed for range-only SLAM, batch optimization methods, and it's even faster than methods like ISAM. So you can see our paper for a quantitative comparison of these. So I guess my point here is just that by using a spectral learning algorithm, we've come up with a state-of-the-art solution, which is actually better than other solutions which roboticists have worked on specifically for this problem. Okay, now I want to look at a totally different example. So, or at least it seems like a totally different example. So here, we're going to look at the problem of modeling video textures. So video textures are basically videos of this natural phenomena, which basically they're like smoke, fire, water, a little bit of sort of wind, wind-activated vegetation, all these sorts of things. And the goal here is that we want to kind of look at short sequences of this data, and we want to learn back a model which will allow us to predict or simulate what future observations might look like. And the way that we're going to do this is we're going to try to model each one of these videos with a Kalman filter model. So it's actually kind of surprising, but Kalman filters are actually very, very good models for this type of data. So a Kalman filter is just a stochastic process with Gaussian state and observations. And as we'll see, it does work remarkably well. So let's talk a little bit more about Kalman filters. So Kalman filters are based on linear time invariant models with this graph structure here. So there's this latent state x, and it generates observations y. The state at x at time t plus 1 is just going to be a linear function of the state at time t, plus some noise, which is sampled from a Gaussian distribution. And the observation at time t is a linear function of the state at time t, again, plus some Gaussian noise. So we have this transition matrix A, or this linear function which updates the state, and the observation matrix C, the linear function which allows us to predict observations. And we can look at, so for the Kalman filter, often we think about things like the expectation of the latent state. So the expectation of the latent state is just the expectation of that state given previous observations that we've seen. We can also consider expectations of observations in the system. So what's the expectation that, of the observation at yt plus 1, given we've seen all the observations up to this time point. And you can see that if we try to predict the observation at time t plus 1, it's basically a linear function of our prediction of the state at time t. So we apply the transition matrix to go one step in the future, and then the observation matrix to predict the observation. Now, if we look at predicting several observations in the future, we see that we can do this with the linear dynamical system parameters A and C. So we can just kind of generalize this to predicting several more steps in the future, right? So if we want to predict 2 steps in the future, we just apply the transition matrix twice. If we want to predict n steps in the future, we apply n times and then apply our observation matrix to make the prediction. So from a current state, we can actually make predictions of whole sequences of observations using something called an observability matrix. And this matrix here, I'm going to call it gamma, which will give you some hint as to what it might correspond to, is basically just a collection of these various prediction steps, right? So this gamma, when it's applied to state, predicts sequences of future observations. And given a large enough number of predictions, the rank of gamma times x hat for a large amount of data will equal the dimensionality of the Kalman filter state space. So we see, again, if we're looking at observation or predictions generated by a Kalman filter, it factors in exactly this way. Right? We have a low dimensional state space and some basis gamma. And we're now back to our original idea again, right? So here, what we can do is we can predict, for a Kalman filter, we can predict our y hat, which is just predictions of future sequences of observations given past observations. We can do that prediction with linear regression, and you can prove that when you make the prediction in this way, this should factor according to the observability matrix and Kalman filter state estimates. And there's actually kind of an interesting recursive proof of this in Van Overschie and De Moor. And if anyone's interested in that, I can point them in that direction later. But that means that we can, again, use precisely the same spectral learning algorithm to learn the state space of this particular dynamical system model. So we just use the same algorithm. But one of the differences, I guess, between this problem and the range-only SLAM problem is we also have to consider dynamics, right? So in range-only SLAM, we really only cared about, where is the robot and where are the landmarks? So learning kind of the bases and our position in the world. Here, we also care about trying to predict what will happen possibly many steps in the future, or trying to simulate future observations. So how do we estimate dynamics? Well, what we're going to need, because this is a stochastic process, we're going to need Bayes' rule. And the basic idea, just actually in general for really any stochastic process, if we have access to the current state, the expected next state, and observations, we can usually learn a Bayes rule update. And you can show this for Kalman filters, for hidden Markov models, for input-output hidden Markov models, predictive state representations, a whole bunch of different models. So that's precisely what we're going to do here. So we've already seen how to recover a linear transform of the Kalman filter state space. And so here, y1 through n, these are just going to be predictions of the next n observations given some history. And again, we saw this is how you recover the Kalman filter state space. We can also get predictions of the next Kalman filter state in a very similar way. So all we really have to do is we just predict sequences which are one step extended in the future. And using the same learned bases, you can basically show that the expected next Kalman filter state can be written in terms of some similarity transform of our dynamics and the current state. So we can get back a linear transform of the current state, and then by predicting the expected next Kalman filter state, this is just the dynamics applied to the current state. And you can use this fact plus a few just linear operations to recover a dynamics matrix which allows you to update this state space. So it's actually very straightforward. It's just algebra. For finding all the parameters which are required for the Bayes rule update, we also need our observation matrix C. We can learn it in a very similar fashion, and we can actually learn all the rest of the parameters of the Kalman filter, including the sort of noise covariances and all that stuff, using very similar strategies. So you just apply a bunch of linear regressions, and you can get all of these parameters back, and this allows you to implement a Bayes filter for the Kalman filter, or a Bayes rule for the Kalman filter. Okay, so let me just return to our data now. So I've talked a little bit about how you can use spectral learning and the same sort of strategy to find a state space in order to learn parameters of a Kalman filter. Now we just want to apply it to our video data. So here, this training data is about 100 frames of video. Our observations are just going to be raw pixels, just a vector of reals over time. And our predictions are just going to be like a sequence of 10 frames of that data. So we can compute linear estimates by just predicting like 10 future frames of the video from 10 previous frames of the video. That gets us a bunch of linear estimates. We apply our spectral learning algorithm, the state space factors. We can then learn the Bayes rule parameters, and we have a model. And given this model, we can filter, we can predict, we can simulate. And here's a simulation from the learned model. So, and you get very similar results, which, if anyone's curious, I can show you later for the other dynamic textures that we were looking at. So you get very, very good simulations. And again, it's using essentially the same sort of spectral approach to learning the state of a system. Now, in fact, learning Kalman filter models in this way via the spectral learning algorithm is kind of the gold standard for learning Kalman filter models in control. So people have been doing this all the way back to like 1987. There's many sort of variations of this standard approach, and FORCID is a very popular one or well-known one. So I just want to kind of point out that many different types of data with different types of observations have been learned in this way. Okay, so now let's look at our final example. So this is a depth camera looking at the observation or the manipulation space of a manipulator. So our goal here is going to be to learn a predictive model of the depth camera looking at the manipulation space of this arm. So this is a 7 degree of freedom Barrett-Wham arm. The arrows here show the various degrees of freedom of the arm. The arm is controlled by setting the 7 joints into different configurations in the configuration space of the arm. You can just see sequences of motor commands here. Basically, we were just motor babbling the arm, so it's essentially just a random walk in the arm's configuration space. Note that the input is continuous. The actions that we're taking are 7-dimensional, and this can move the arm sort of all around. I want to talk just a little bit about error in the arm. So just because you set the arm to a particular configuration doesn't mean that the arm is actually in that configuration. So although the WAM arm is considered to be very accurate, there is error in its internal estimate of its joint configuration, and you can actually show this. So Sid in robotics, he has a setup where his WAM arms have both motor encoders and joint encoders, so we can actually look at the difference between what the motors are telling us for the arm's position and the actual position of the arm. So you can see that there's error in the arm's configuration. And on the bottom here, you can actually show this where you tell the arm to put the end effector in the same position. It tries to do this several different ways, and it turns out that that position ends up being different for all the different ways that you sort of arrived at that configuration. And the reason for these disparities has to do with unmodeled physics in the arm. So basically, the arm has this problem of cable stretch. So there's cables which are controlling the movement of the arm, and they wind at different tensions based on previous arm torques. So there's this kind of path dependency, which tells you, maybe gives you some information about what the actual position of the arm is, given its previous configurations, the amount of torque applied to a joint. Okay, so that's the arm. Observations are generated by a Microsoft Kinect depth camera, which is looking at the manipulation space of the arm. The Kinect produces RGB images and depth images at 30 frames a second. The depth camera in our experiment is basically set up at on a table looking directly at the arm. I should note that the depth camera is fixed, and when we're moving the robot around, the whole robot sometimes shakes, which adds additional error in our observations of what's happening with the arm and where it is. All right. So together, the arm motor babbling and the Kinect depth cam generate observations which look something like this. Again, example motor commands are shown below. So we just move the arm around like in this space. We're basically saying move the end effector around randomly within some fairly constrained space. And our question then is, can we learn a model of this depth camera information directly from these actions? And so we're going to, I mean, I guess I just want to say that sort of in this problem, this is sort of actually, this is directly like the critter learning problem, right? Like this is, you have this high dimensional observation, you're moving something around, and like you just want to predict what you're going to see in the future without using any of the physics which might be behind this. So that's what we try to do. Okay, so we're going to think of the state in this case as a probability distribution of future Kinect images given future actions and past data. Unfortunately, coming up with an expressive representation for continuous high-dimensional observations like this is actually extremely difficult. So although we're going to think of state as this like probability distribution over the future, this is a very nonlinear, non-Gaussian system, so it's going to, we can't use a Kalman filter. We've tried that. It looks horrible. So we need a different approach. And the approach that we've taken is based on predictive state representations. So usually predictive state representations assume a small set of discrete actions and a small set of discrete observations. The state is represented as basically a bunch of conditional distributions of sequences of future observations given sequences of future actions and given a history. And we then just update the state using Bayes' rule. The problem, of course, is that these are not small sets of discrete actions and observations, but continuous, really high-dimensional actions and observations. So we basically had to develop new models which will allow us to handle this. So we want to try to handle continuous arbitrary distributions of actions and observations and be able to reason about those with a new model. So this was the goal. We developed a method for doing this, a non-parametric method called Hilbert space embeddings of PSRs. The basic idea is that we represent state as embeddings of probability distributions, basically embeddings of probability distributions over future observations given actions in a reproducing kernel Hilbert space. So these are just expectations in some function space. And we then update state given a new action, a new observation using kernel Bayes' rule. So obviously, I don't have enough time to go through all the details of how you do this. That's like an entire additional talk. But there are a couple of problems we have to solve here. Essentially, we're kind of reasoning about probability distributions with infinite dimensional operators. So how do we do this in practice? Well, we use the kernel trick and represent the operators implicitly. Distributions are embedded in RKHS, so how do we make predictions when we have like one of these embedded distributions? Well, we use kernel regression, which allows us to recover moments of these embedded distributions, and we can use kernel density estimation to try to reconstruct the distributions if we want to, although we generally do not do that. Finally, I just want to note that depending on the kernel that we use or the representation that we use, the eigenspectrum of our predictions may scale with a number of training parameters. And this means that our state may actually be infinite, and it's not easy to compress it down to a lower dimensional state, right? So, I mean, I guess in practice it could be actually just as large as the number of training data points we have, but so that's not good. But depending on our choice of kernel, we can actually still use a spectral learning algorithm. So for example, if we learn a kernel, or we use a kernel which is appropriate for, let's say, manifold learning, you can actually learn low-dimensional representations of state using a spectral learning algorithm. And the learning algorithm basically looks like this. We implicitly predict future sequences of observations, and we represent them as these embeddings in RKHS. We implicitly build empirical covariances of predictions, and this is just represented with gram matrices. We factor using kernel PCA, and then we can recover a finite dimensional state space in this way. So I know I've been somewhat vague here. If you want to learn more about these kind of non-parametric approaches to learning dynamical system models, go to my website, and there's a whole bunch of recent papers we've had on exactly this, this approach. The important takeaways are just that we represent distributions of future connect images in response to actions as embeddings in an RKHS. These are represented implicitly as weights on training data samples. We update everything with the kernel version of Bayes' rule, and we can predict expected connect images via regression from embeddings. So that's really all I'm going to say about this approach. I do want to show you some results. Basically, we tested data by filtering and predicting on never-before-seen actions and observations generated by new random trajectories through our manipulation space. So we generate totally new trajectories, and we see a whole bunch of data that we've never seen before. So the first thing I'm going to show you is filtering. And so what we have here are basically two things that we can look at for our distribution. We're now filtering based on the action that we take and the observation that we see. We can generate our expected observation from our distribution, which is represented in the RKHS. And we can also look at what the model says is the closest training data point in our training data set. So this is an extremely high dimensional space. You'll see the map observation kind of jumps around a lot. The next thing that we try to do is so we showed filtering, and you can show that it kind of tracks what the manipulator is doing fairly well. The next thing we do is we start from filtering, and then we try to predict into the future using just sequences of actions and no observations. And we show essentially how well we're predicting versus the true observations that the Connect is seeing. So I know that was a little bit difficult to see and went pretty fast, but you can take a closer look at what's happening here. So each image here is an expectation of the embedded distribution of depth images. On the top row, you have filtering. So you'll notice that in the first image here, it's very, very blurry. You really have no idea kind of where the arm is. As you take actions and receive observations, you can see that our expectation is becoming clearer. And this basically means that the distribution, like the weights are shifting to just a few sort of images in a training data set, and the distribution is concentrating now on a specific set of training data points where it thinks the arm is. Sort of the opposite thing is happening when predicting. So when predicting, we're just feeding actions to the model, and we're not feeding any observations. And you can see over time, as you predict farther into the future, the expectation of where the arm is gets a little bit more diffuse. Okay, so I'll very quickly go through these quantitative results. Basically, what we did is we compared our model to kernel regression. So we do have sort of this noisy estimate of state, which is what we're using as the actions, right? The configuration of the robot arm. And the idea is we're just trying to directly predict what the the depth cam sees from our current configuration values. And so that's what the kernel regression is, this top row here. Basically, what we want to show and what we do show, this is, I think, over 1,000 different examples, so we've tested this fairly extensively. We show that our dynamical system model, essentially, as it's filtering, starts predicting the observations better and better than kernel regression, based on, essentially, the past information that's accumulating over time from the previous actions and observations that it's taking. So it's exploiting the fact that the previous path that you've taken through space actually tells you a lot more about where you currently are than just like your current action command. And then when we do prediction, you see that you get worse and worse, but we never do worse than kernel regression. So this is good. It means that the dynamical system is better than just doing kind of non-parametric regression. And when we predict farther into the future, we get worse, but no worse than just doing kernel regression. OK. So in summary, basically, I presented a spectral learning framework, which relates the eigenspectrum of predictive moments to the inherent structure in the process which generated the data. We've applied this framework to attack this old problem in artificial intelligence, the critter problem, where the goal is to learn a generative model of observations given actions for essentially any sensor, actuator, or environment. And spectral methods, again, think of prediction of state as predictions of the future, and update state using Bayes' rule. And this is in contrast to most robotics approaches that try to model the physics of the system. And we've applied it to a variety of high-dimensional systems. So, by the way, if anyone wants to ask me about any of these other systems that we've been looking at, the hawk moth is very cool. Feel free to ask me after the talk. OK, so finally, I just want to talk about a few related papers. We had this range-only SLAM paper, which describes that work. This was in ICML this last summer. Video textures, that work was described in a paper we had in 2007. And the current work on the depth camera and manipulator is based on work that we published this last summer at UAI and work which is currently under submission. Finally, we've tried to learn models of all sorts of other things, including pendulum video, learning agent moving around in a simulated environment and then planning in the learned model, learning a model of a camera on a robot, and modeling a slot car. So all of these are different types of robotics and robotics-like systems that we've modeled with spectral learning algorithms. Finally, I just want to kind of plug the general idea of spectral learning. It is sort of a new up-and-coming field. Recently, it started to take off, so there was this tutorial on it at ICML 2012. There was a workshop at NIPS 2012, one at ICML this last summer, and there's another one this winter at NIPS. And ICML this last summer also had a dedicated session to spectral learning, and there was another tutorial at that ICML as well. So it seems to be gaining momentum, and more people are looking at these approaches to solving difficult machine learning problems. Finally, it also has garnered several Best Paper and Best Paper Runner-Up awards at recent conferences. So, all right, thank you very much. Yeah.
I have a couple of questions about
sure.
applicability outside robotics.
Yeah.
I'm interested in educational data mining.
Yeah.
So one part of the question is, what if you're observing tutor-student interactions and you're trying to discover a model distribution? And the other part is, in these examples, the observations were vectors. They're feature
That's right, yeah.
What if your observations or your events are essentially structural data?
Okay, yep. So these are actually both very interesting questions. So I think the first question is basically what happens when you have some sort of like interacting system, right? Like a teacher and a student, and you want to learn a model of one or the other. So first of all, basically today I only presented work on that I've been doing in robotics, but spectral learning algorithms have been used in educational research recently. I know several people, including Jeff and Emma, are looking at using them right now. So it's definitely applicable there, and I think there is a lot of recent interesting work, and there will continue to be interesting work at looking at these sort of interacting systems, both in robotics and in other domains like education, where You might actually want to learn a model of the student or the teacher or both and how they interact with each other. Or in robotics, learning from demonstration problems often take a form like this, where you have, where you actually demonstrate what the robot is supposed to do. Or maybe you're looking at interacting systems where you're demonstrating one thing and the robot is responding a different way. So there's a whole bunch of kind of different ways of looking at, or there's a whole bunch of interesting problems where you're looking at the interaction between like two processes. So yeah, I mean, it's a great area of research and people are working on it. As far as the type of observations, spectral learning algorithms in the past, so a lot of the recent work is actually for discrete observations. I am particularly interested in continuous valued observations, vectors. This is basically just because of the domain that I work in robotics, but you'll find if you look at sort of the wider spectral learning literature, most of the work is for discrete observations and for that type of domain. So there is a lot of work happening there. So for example, hidden Markov models, and now there's a whole bunch of work in trying to learn probabilistic context-free grammars and actually a whole sort of range of different types of latent variable models, latent Dirichlet allocation, a whole bunch of stuff where they're using spectral learning methods and the observations are basically discrete. So, blue shirt. That's you, yeah.
Can you, like, can you link spectral learning to guide the robot to explore the portions of the space where it's more ambiguity?
Yeah, maybe. I mean, yeah.
Such a link has been established?
Well, I think no, I don't think anyone has, at least that I know of, I don't think anyone has really looked at that. Of course you could do it though, right? So what I've talked about is basically learning models of systems. So these could be like continuous dynamical system models. They could also be models sort of like input-output hidden Markov models or POM-DPs. And of course, you could do a lot of really interesting work on trying to figure out essentially how to guide your search for new observations and new data in order to build more complete models, right? So I think it's wide open. I mean, we're trying to learn models of dynamical systems, and you kind of want to get as much experience as possible, and guiding that search would be very useful. Yeah.
In your third example, I think you mentioned that it wasn't really a low-rank matrix.
Yeah.
What's your sense on, in settings like that, what's your sense on what spectral, what you can
Okay, yeah, so let me say a few things about that. So first of all, so like if you're using a Gaussian RBF kernel or something like that, you can't really expect your eigenspectrum to converge to a finite sort of fixed set of eigenvalues, right? Instead, it sort of precipitously drops off, and I think there's some interesting questions which are, as far as I know, fairly open about what happens when you kind of cut off the eigenspectrum at some point, and how accurate is the resulting model. I don't know.
Your example,
yeah.
Did it precipitously drop off, or did it really just go flat?
So yeah, so I mean, obviously I skipped many things when I was talking about that last example. For our data, so we did have to, so what we did, like the amount of data we collected was actually quite large, right? We collected about 60 gigabytes of data, and then we had to essentially use some approximation techniques to reduce that amount of data because it's a non-parametric method, and you just have to do that, at least with today's computers. So we use some fairly standard techniques. I mean, some of the things we looked at were using incomplete Cholesky decomposition to find like good sort of sets of training data, and you can also use kernel PCA or kernel SVD in order to find a low finite dimensional space. In which case, we're just chopping things off, really before the eigenspectrum has declined very much, just from computational necessity. Now, but the other thing I want to say is that depending on what kernel you use, so for a Gaussian RBF kernel, it sort of slowly goes off to infinity, and there's no clear cutoff. But if you do use a kernel like the types of kernels which are used in manifold learning, those actually often do have an eigenspectrum which does appear to be converging to some fixed finite set of eigenvalues. And this is just sort of an assumption you can make. So I mean, whether you should use one or not and what that means in terms of spectral, I mean, it just is like it's a choice and it depends on the problem. Yeah. Yeah, and then I'll get to you. Yeah.
So in the models you were learning,
Yeah.
you sort of had one set of dynamics that you were looking at. Do you have any thoughts on how this might apply to either being able to do change point detection or looking at multiple sort of models that are happening? So for example,
Sure.
A data set of people exercising and doing different exercises.
Yeah, so I think that's a fairly open question. I actually have some ideas along this line, but let me just say two things. So first of all, the idea that you're using linear dynamics, or maybe you can think of it as like bilinear or even trilinear dynamics. You have some dynamic model which has which is linear, which is either linear or like maybe bilinear in the state and observation or something like that. That's a general. I guess those types of models, although they seem restrictive, are actually fairly expressive. And they're expressive because linear models, as we know, if you use them in other types of feature spaces, end up being very powerful and being able to model nonlinear things, especially if you move to kind of infinite dimensional spaces. So sort of the restrictiveness of linear models is somewhat open to debate. I mean, you can model all sorts of nonlinear things. Now, you were suggesting that something like switching dynamical systems or sort of switching state space models might be something which is very useful, and I agree. I think that that research question is open. I know that so we have good dynamical system models for hidden Markov models and for POMDPs. We also have good dynamical system models for linear dynamical systems. So kind of an obvious question is, can we combine these? Can we get some sort of switching system where you can instantly switch from one set of linear dynamics to another one? It's an open question. I think it can be solved. I think someone will do it soon. Maybe me. We'll see. So yeah.
So you said that you are trying to replace this notion in robotics that instead of getting a physical model, now that we can get data, let's do a data-driven thing. Is there a middle ground with spectral learning where you can kind of enhance, or leverage what you know about the physical system instead of?
So exactly. So like if you're a roboticist and you know a lot about the physics or the geometry of the system, like it seems extremely wasteful to just kind of like throw all that away when it could constrain your search for solutions. And I guess my view on a middle ground would be something like the range-only SLAM problem, where we do understand the geometry of the problem, but we also want to come up with like a good learning algorithm. And so often what happens is someone who understands sort of the geometry or physics of the problem can kind of help write down what the right sort of predictions to make are in order to learn this low-dimensional state. So I think there's still space for people to use expert knowledge basically to kind of guide the creation of the spectral learning algorithm. Although I must say, ultimately, I am interested in sort of just saying, I don't care about the physics or the geometry or whatever. Maybe it's actually extremely difficult to write that down. So it might actually be better or more interesting to try to just learn everything. And the idea is to come up with a model which is sufficiently expressive so that we can do that. So I mean, I guess my hope is that like the WAM arm, it's a fairly straightforward manipulator. I mean, it's a very simple kinematic chain. But you can imagine all sorts of different types of robots or systems that you might want to control, which are not so easy to model. And I think that's kind of ultimately where we're going. We want to be able to learn models of systems where it's just not clear how to write down the physics or geometry. Yeah.
You mentioned that there's an infinite number of representations because of this.
Sure. Yeah.
And there's an issue of interpretability. Can
Yep.
you say something more about how to take these entirely empirical models and try to make them do sense?
Sure.
Domains, for example, educational
Sure.
data mining, where the extent to which you believe the model is going to be highly influenced by
Yep.
what you understand what the model is saying.
Yeah. So so I think you're absolutely right that from an from an interpretability standpoint, that may be critical. And what's I think interesting is that in different domains, people have sort of come up with different methods for doing this. So we came up with a specific method which looks at, essentially for range-only SLAM, we came up with a specific method which fits a bunch of surfaces to things, and it turns out you can recover sort of a metric map which is true up to some like rotation, translation, and offset. So, but the way that we solve that problem is actually different than, let's say, how people, so these methods are also related to structure for motion, and there's a way to do a metric upgrade there, which is essentially solving that problem as well, and that's just different. Like the way they do it is different, and it's domain dependent. Now, there's a whole bunch of new spectral learning algorithms, basically in the last year, for learning hidden Markov models, where you want to actually learn a low-dimensional state space and a transition matrix, which actually correspond to the sort of original parameters of the HMM. So you want to have a stochastic transition matrix, and you can do this by looking at higher order moments of the observations. So you can do basically a tensor decomposition instead of an eigen decomposition, and this gives you kind of enough information to sort of unravel that similarity transform and get back the original model. Now, unfortunately, the thing which is kind of true about all of these different methods is that they're like all different from each other, and they're all somewhat domain dependent. So coming up with kind of the right solution to that may be a domain dependent related question. One thing you could do is if you do have a little bit more information, you can just try to do it via linear regression. And so for example, for the range-only SLAM, if you know where a couple robot positions are or a couple of the landmark positions are, you can easily just learn a similarity transform via linear regression. Regression is one way. It's kind of like the wrong way to solve the problem, but it might give you something like some interpretability. But often for the various domains, you need people have different methods for doing this. So I don't have a good solution for your domain, but again, it might be a very interesting open question. All right, thanks.